In this video, we'll talk about computing the surface area of solids revolution, but also for parametric equations. So the idea here is the same as it was before. I'm going to chop my curve up into little lengths, and I want to rotate those lengths around the x-axis to give me the boundaries of little cylinders. And then if I add up those shells, that will give me the surface area of the solid revolution. The idea here is the same. If I have c of t being my curve, y is always positive, which I need for doing a solid revolution. X of t is increasing, also for solid revolution. And x prime and y prime are continuous. That's what I need to do the mean value theorem part for the length of the curves. Then I can get the surface area by rotating c of t around the x-axis by surface area S is going to be the integral from a up to b, 2 pi, the radius, which was my function f of x before, but now it's the height, so it's y of t. And then the length, which stays the same, square root x prime of t squared, y prime of t squared, dt. And you would think about this in the same way. This is again 2 pi r times h, or 2 pi f of x root 1 plus f prime squared, which were the functions we had before when we were doing for functions, but now we just have to convert the notation into parametric equations. What's f? Well, it's the y coordinate. And how do you get length? It's x prime squared plus y prime squared. And again, all these conditions matter to make sure you actually get a valid solid revolution while you're going about this process. Same thing we needed before for talking about integrals and lengths of curves. We did not double back on ourselves. We did not do anything weird to not get an actual solid revolution here. So as an example of this, we're going to find the surface area of a surface generated by revolving c of t is cosine cubed of t sine cubed of t between 0 and pi over 2. Now, if I had gone over a longer range, I would have had repeat problems, or doubling back problems, but because I'm staying between 0 and pi over 2, this is all entirely fine. So, let's just set up and see what happens here. So my surface area should be the integral from 0 to pi over 2 of 2 pi times y of t, which is sine cubed of t, times the square root of x prime squared plus y prime squared. Now, in this case, x prime is what? It's 3 cosine squared of t sine of t with a minus sign. And y prime here is 3 sine squared of t cosine of t, both of those done by the chain rule. Now, I can then square each of these and put them in the expression. I will get that s is the integral from 0 to pi over 2 of 2 pi sine cubed of t square root of 9 cosine to the fourth of t sine squared of t plus 9 sine to the fourth of t cosine squared of t dt. I can now factor out a cosine and a sine from the square root because both terms have a cosine squared sine squared in them. What that will give me is integral from 0 to pi over 2 of 2 pi sine cubed of t. I then get the cosine of t I factor out, the sine of t I factor out, and the 3 that I factor out with the 9, square root of, the first term has a cosine squared of t left over, the second has a sine squared of t left over, dt. This radical is now 1 because it's cosine squared plus sine squared, that adds to 1. That goes away, and I'm left with s being the integral from 0 to pi over 2 of now 6 pi sine to the fourth of t cosine of t dt. This falls into our trig integrals category, but thankfully it's an easy one. I can set u to be sine of t. du is then cosine of t dt. So my s becomes 6 pi, the integral. If u is sine of t, then at 0, I get 0. At pi over 2, I get 1. I get u to the fourth du, which I can then integrate and solve. 6 pi u to the fifth over 5 from 0 to 1, which just gives me 6 pi over 5, which is the surface area of that solid revolution. And that's how the calculation works out. And that's the sort of point of this idea is even if I have a parametric curve, I can still do solid revolution and still find their surface area by similar techniques to what we had before, just now modifying the formulas to now work with parametric equations. That's really the theme for this section is I can do everything I want to do still with parametric equations. I have to make sure I modify my formulas appropriately to fit that equation and not just base it on ones that are from standard functions. As long as I do that, that will work just fine for doing lengths and surface areas of curves defined by parametric equations.